Hi, everybody. So this time we're going to go over different properties of determinants in order to show you a way to go and find an easier way to compute these things. Now, what we would like then is, since we know that there are certain operations we already do with matrices, like row operations, we'd like to know how the row operations interact with the determinant. Also, since we have certain computation techniques or rules on matrices, like how to add matrices, how to multiply matrices. We'd like to know how the determinant interacts with those. So we'll handle the first one. How does the row operations deal with or interact with the determinant? So first, a goal. We want to have a row reduced echelon form, or at least an echelon form. So why is it being? That if you have either an upper or a lower triangular matrix, or a diagonal matrix, because a diagonal matrix is both, then the determinant is actually just the product of the entries on the main diagonal. It's really easy to see by just doing a proof by induction. I'm not doing those things. I'm just going to hand wave and go, well, look at this example, see how it's true. So for this matrix, which is clearly upper triangular, go ahead and expand on the first column. So this would then be right here. That's the first column. That's me expanding on it. Now, but in the first column, the entries are 0 except for the entry on the main diagonal. So all those cofactors, these cofactors here, none of them matter. So we have 1 times the cofactor C11, which I wrote down as a determinant. But then notice that is also upper triangular. So I can repeat the process. Look at the first column and then find the cofactor expansion on that. So then you'd get 1, because we had 1, plus this sum of multiples of cofactors. But once again, a whole bunch of the entries in this product are just 0. So that doesn't matter. So I just get 1 times 2 times C11. See how it's a theme? I keep getting C11 back. So this times C11, though, is the determinant of a 2 by 2 matrix, 5, -1, 0, 2. And we know how to find that determinant. Just take the product of the entries in the main diagonal, and then we subtract those products. So we have 5 times 2 minus 0, which is just 5 times 2. So the determinant then is just the product of 1, 2, 5, and 2. Those were the entries along the main diagonal. So that's really nice. That lets you find the determinant of a matrix that's in row echelon form, at least, very quickly. So this matrix is at least in row echelon form. Its determinant is just find the entries on the main diagonal and multiply them together. That thing's 15. Done. Nice. Now, there's also another property that's incredibly easy to see. If you ever have a row of zeros, well, then the determinant has to be 0. Just find the cofactor expansion on the row that contains all the zeros. All the entries are 0. It doesn't matter what the cofactors are. It'll be 0 times a cofactor. It'd be a sum of zeros. That's 0. So that's also a pretty easy result. If you ever have a row of zeros, or a column of zeros, actually too, if you want to, then the determinant actually is 0. Now, this next one, yeah, we're not going to prove it. This would require a serious amount of induction. Instead, I'm just going to go, look, it's true, by looking at examples. I'm not interested in spending probably 15 minutes, 20 minutes proving this thing. So instead, if you ever take any 2 rows and swap them, the new determinant is the opposite of the old determinant of what you used to have. So I'm showing you 2 examples. If you take the matrix 1, 3, 4, 2 and swap the rows, then the determinant of the result is opposite the determinant of what you started with. Notice all I did was swap 2 rows. Here, 3 by 3, if you just take 2 of those rows and just swap them, it's just the new determinant's opposite what you started with. So that's really great. So we can swap kind of willy-nilly, and all you ever do is put a minus in front of the new determinant. That's great. So why is it true? As I said, because we're not going to prove it. This is one of those things that's it's real pain in the butt to actually write out. We're not really interested in doing so. So, but that means then, this one we will prove, that if any 2 rows are exactly the same, then the determinant has to be 0. To see why, it's a clever use of what I just showed you of swapping rows. So let's really quickly prove this one. So suppose you have 2 rows of A that are identical. Just swap them. That'll then form another matrix B. But these two rows are the same, which means that A and B are the same matrix. So if they're the same matrix, then their determinants have to be the same. But I also just said that if you ever swap rows, the determinant of the new matrix is opposite of the determinant of the matrix you started with. So then the determinant of B and the determinant of A are actually opposites. Well, if they're equal and they're opposites, that can only happen in one case. That means that the determinant has to be 0. And that's it. Nice, right? Really easy stuff. So if you ever have two identical rows, the determinant is automatically 0. Don't do the computation. So like here, there's two rows here that are the same. So then that determinant is 0. Don't do all the computations. Now there's another neat consequence of that, which is really kind of subtle. If you ever do a cofactor expansion using the cofactors of one row, but the entries of another, that's always 0. That has to be 0. The reason is just, you can see it by doing an example. Take this one matrix. I'm going to do the cofactors from the first row, but I'll use the entries from the third row. That will then give you this. So that's using the third row for the entries, but the first row for the cofactors. But you should recognize that that thing is a determinant. It's actually the determinant of a certain different 3 by 3. It's actually the determinant of this matrix, where you just do the cofactor expansion on the first row. And in this new matrix, notice that the first and third row, they're the same. So the determinant, of course, is 0. That's why if you ever do a cofactor expansion, but where you use entries for one row, but the cofactors from a different, it's always going to be 0. It has to be 0. All right, so let's go look at the other row operations. If you ever take a matrix and it's the result of multiplying a row of A by K, then the determinant of the new matrix is K times the determinant of the old. Once again, this deserves an explanation, so I will explain it. Let's suppose that B here is formed by multiplying the ith row of A by K. Notice I'm defining the entries of B and A using lower skip versions of the same thing. So that means then for all K, I use K twice, for all indices, doesn't matter what this index is, I'll call it, I just call it something else. Let's call it for all J, the cofactor of A is the same as the cofactor of B. The reason the ith jth cofactor of A is the same as the ith jth cofactor of B for that fixed I is because the matrix A and B only differ on the ith row, right? On the ith row, B, that matrix, the ith row is just the ith row of A multiplied by K. So in every other way, A and B are the same. And when you find a cofactor for the ith jth cofactor, you're wiping out the row that they're different in. So of course the cofactors are the same. But that would then mean that if you want to find the determinant of B, you would do a cofactor expansion. We'll do it on the ith row. So then that would be what you see right here. But remember, the ith jth cofactor of B is exactly the same as the ith jth cofactor of A. Also, we know what B is. We know what B sub something is in terms of A on that ith row. So I can replace B sub I1 with K times A sub I1. I replace B sub I2 with K times A sub I2 and so on, because we multiplied the ith row of A to get by K to get the ith row of B. But then notice how they all have a common factor of K. Just take all the K's out. And remember, again, the cofactors, the ith jth cofactors of B are the same as the ith jth cofactors of A. So what this is right here, that's actually the determinant of A. That's just the cofactor expansion of A. It will expand on the ith row, and that's the result. So you need a way to use this thing, and it's really nice. So suppose you start with this matrix right here. Notice how on the first row, there's a common factor of 2. You think of it as, let's multiply the second row by 2. Let's multiply the first row by 1/2. When you do so, you get a new matrix, 1, 1, 3, 6. But what happens in the theorem, it says that in the result, you factor out the k. You factor out that 2. You divide it by 2, put the 2 out front. Doing it again, see how in the second row, there's a common factor of 3? We think of it in row operations as we're going to multiply the second row by a third. But by the row operation, see where the k is and where a and b is? You can factor out, that 3. So then the determinant of 2, 2, 3, 4 is equal to 2 times 3 times the determinant of 1, 1, 1, 2. That's really great. That makes it really easy, at least to use this particular row operation with determinants. It's wonderful. It's like you like factoring things out. It's great. So some basic consequences. If you ever take a determinant of a matrix that's being multiplied by a scalar, what you're really doing is multiplying that scalar to each row, and then afterwards you take that scalar out of each row, but now you're doing it for each row, so that in this case, if it's a 2 by 2, you're doing it twice. So the determinant of a multiple of a matrix is actually that multiple to a power, where the power is the number of rows times the determinant of the original matrix. That's kind of unfortunate. That's kind of unfortunate. We'd like to say that the k just comes out, but it just doesn't. So scalar multiplication doesn't work perfectly with the determinant. Also, we get this other nice result that if 2 rows are ever multiples of each other, then the determinant has to be 0. Like this matrix here, 1, 1, 3, 3, that determinant 0. You don't have to do any of the work. It's because the first and second rows are multiples of each other. If you want to go through y, notice in the second row, we can factor out the 3. Then you have a determinant of a matrix, which is 1, 1, 1, 1. But now the new determinant has 2 rows that are the same. So that's 2 times who cares about the rest. So the overall determinant is just 0. So if you ever have 2 rows that are multiples of each other, that determinant's instantly 0. All right, so now we're up to the third row operation and final one. If you have a matrix that's the result of adding a multiple of a row to another row, then their determinant's the same. That's fantastic, because that's by far the most frequently used row operation. So if you ever add a multiple of a row to another row, the determinant actually doesn't change. That's great. So once again, though, this deserves an explanation. So let's suppose that you have B is formed by multiplying the jth row of A by K and adding it to row I. Then if you look at the ith kth cofactor of A, it equals the ith kth cofactor of B. So along the ith row for both these matrices, the cofactors of A and cofactors of B, they're equal to each other. So the first cofactor is the same along the first row for I and for A and B. The second cofactor in the ith row for A and B are exactly the same, and so on. And the reason is because you're only changing the ith row. You're only changing that one row. So then, of course, everything else is exactly the same. Well then, let's find out the determinant of B. So the determinant of B is then just expanding on that ith row. You'd have B sub I1 times the ith I1 cofactor of B. And then you have B sub I2 and the cofactor C sub I2 and so on. And you add those up. But we know what the entries on the ith row of B are. It is the original, it's the original ith row of A, and then you're adding on a multiple of the jth row to it. So that's written this way. So it's the first entry, B sub I1, is A sub I1 plus that multiple of the jth row. And you just write them all out. Let's take that algebra, just multiply things out. So then you get that. Notice though that then the second grouping I just gave you, there's a common factor of K. Just take that K out. But then notice that in that very last one, that's 0. Because that's a cofactor expansion using the ith row of A, but using the jth row for entries. That's 0. So it's 0 times K, that's just 0. So we have what's left over A sub I1 times C sub I1 and so on. But the cofactors along the ith row for A and B are exactly the same. So therefore, that's the determinant of A. So the determinant of B is actually the determinant of A. This is great. I'll show you how to use it. So what if you had the matrix 1, 2, 3, 8? To that matrix, take 3 times the first row, take 3 times the first row, and then subtract it from the, oh, there it is. Subtract it from the second row. This first row then doesn't change. The second row would then be 3 minus 1 times 3, 0. You get 8 minus 3 times 2, that's 2. So the new determinant would then be 1, 2, 0, 2. And that thing is upper triangular. So we know how to find that determinant. That determinant is just 2, the product of the entries on the main diagonal. Neat, right? Okay, let's just review so you have all the different properties here in front of you. So if you have 2 square matrices A and B, if A is upper or lower triangular, the determinant is just the product of the entries on that main diagonal. Notice that this is also true for diagonal matrices because they are automatically both upper and lower triangular. If the matrix ever has a row of zeros, the determinant is 0. If you ever swap rows, then the determinant of the new matrix and the determinant of the old matrix is off by a minus sign. If you have 2 rows that are equal, then the determinant is 0. If you multiply a row by k to get the matrix B, then the determinant of the new matrix is k times the determinant of the old matrix, the original matrix. If you ever add a multiple of a row to another row to get B, then the determinant doesn't change. And I didn't put the other one in here. If one row is a multiple of another row, the determinant once again is 0. These are really nice. It's really nice to be able to use this in order to figure out determinants. So I'll show you how to use it once by a matrix. Let's look at that guy. It's a 4 by 4. I would never use Laplace transform of the Laplace expansion on this. It would be crazy. So I would not do cofactor expansion on any row or column. It'd just be awful. I would get 4 3 by 3s. Each 3 by 3 would give me 3 2 by 2s. It'd be huge. I have no interest. So instead, we'll do this. Notice that what we can do is along the first row, see that common factor of 2? So I'll take the 2 out. That's essentially saying on the first row, divide it by a half. We think of it in terms of determinants as pulling out the 2. Then let's use that first row. I'm going to add the first row to the third row. I will take 2 times that first row and subtract it from the fourth row. When you do those row operations, the determinant doesn't change. So the row operation doesn't change the answer, just write down the new determinant. And we have that then. Notice that we're slowly turning it into an echelon form. All right, now take that matrix. What I want you to do is in the second row, I want you to subtract it from the third row and take the second row and double it and subtract that from the fourth row. That then does not change the determinant. You still have a 2 times a determinant of the new matrix. But then in this new matrix, notice that I can take the third and the fourth row and swap them. When you do that, you have to put a minus out front. So there you go, putting a minus out front. But then the new determinant is of a upper triangular matrix. I just take then the product of the entries in the main diagonal, and the answer in the end is -2 times 1 times 2 times -5 times 1, which is 20. That's the answer. That's the determinant of the original matrix. Neat, right? Now, if you want, you don't have to put the row operations in. I did that just so you can see what I'm doing. But lots of times we don't include this stuff. You can, and I think it's wise to do so that if you make a mistake, you can figure out where your mistake was. It's also nice for a reader so that I know what you were thinking. So it's easy for me to check your work, but you don't have to. Notice though that if you want to do this on a calculator, you can't, because the calculator does not keep track of the row operations for you. It automatically just takes the matrix and gives you back the row reduced echelon form. So then you can't use this technique on a calculator, at least unless you want to do it each row operation manually on the calculator. So it's probably not worth your time. So that's enough, I believe, for this video.